In this video I have converted a Hot Wheels size car into a radio-controlled car. The model car I have selected is Tomica Lexus RCF in 1:64 scale. Tomica is a Japanese die-cast model car manufacturer. Unlike Hot Wheels, Tomica cars are made much more accurate and are true to scale. The dimensions of this Lexus RCF are length 73.5 mm, width 28.8 mm, and height 21.7 mm. Before starting this build, I have set few rules. Firstly, the car must have proportional throttle and steering. The placement of wheels and other components should have good precision. And at last, the structure of the car should be robust and very reliable. The video is divided in 4 parts. The first part will cover steering mechanism. The second part will be about powertrain. In third part we will install electronic components and finish the build. And the last part will be a small test run. So, let's begin. For the wheel assembly, I have used Spectacles hinges. This part of the hinge fits perfectly inside the bearing. It will act as a steering knuckle. After creating an attachment point for tie rod, the wheel assembly is almost complete. With everything bolted together, we could mount the bearing on it. Let's check if everything works properly. The steering axis for this wheel assembly will be a line passing through the center of the screw. The steering axis is the axis around which the wheel assembly swivels as it turns to the right or left. The distance between steering axis and tire center line determines the scrub radius. Low scrub radius has many advantages, like wheels occupies less space while turning left or right, and the whole mechanism looks realistic. I have placed the front axle onto this chassis and reinforced it with high-strength epoxy. This is a 3.7 gram servo motor. Of course, to save space I have reduced it to only essential parts. Let's test this to see if it works properly. For the rear axle, I have used a shaft and brass bushing from the FA 130 motor. The 9mm bearings will be used as rear wheel. This is N20 motor, it will be used to power rear wheels. The N20 motor is commonly used in standard 9 gram servo motors. I have made a reduction gear box. This reduction gears are arranged to achieve ideal balance between torque and speed. I have placed the axle on chassis and reinforced it with high-strength epoxy. This car does not have suspension, but it is worth mentioning that all 4 wheels touches the ground strictly in same plane. It took me multiple attempts to achieve this low tolerance in placement of wheels. This setup does not require a differential gear at rear axle. Because steering mechanism is designed in a way that it eliminates the need of differential gear, it helps the car to oversteer in turns at high speed and make a smooth curve at low speeds. The design also eliminates the requirement of suspension system. All these effects are achieved by many factors. It will take a whole new video to explain it all. So, as of now let's focus just on contribution of steering mechanism. When wheels are turned to left or right in a curve, the weight of the car is redistributed on diagonal wheels. In a curve the inner front wheel and outer rear wheel has more weight. Few other factors make both front wheels to gain traction, which help the car to turn. Meanwhile, the rear inner wheel experience complete loss of traction due to no weight on it. This eliminates the need of differential. I am using Turbo Racing RX41 receiver and P32 transmitter. I had to disassemble the receiver to save space. Meanwhile I have made a compact switch mechanism and charging system using JR Futaba connector. A small copper clip will slide back and forth on the copper pins and toggle the switch on or off. The charger is TP4056 module, in which we could plug micro USB. This project now requires only 3 more components. The first is battery. I'm using 2 of 3.7V lithium polymer batteries connected in parallel. The approximate size for one battery is 21 mm length, 8 mm width and 4 mm thickness. The second component is speed control unit for rear motor. This speed control is also removed out of the standard 9 gram servo motor. And the third is PCB from receiver. I have attached the receiver PCB and speed control unit onto the steering servo with a medium strength epoxy. The batteries will remain loose and could be pulled out from one side if they need replacement. The battery compartment could accept the battery size up to 24 mm length, 8 mm width and 9 mm thickness. These two batteries are connected in parallel, so nominal voltage will remain same as of one battery, but we will have double amperage to feed the drivetrain. And this is how it looks after wiring everything together. To save spaces, have used a special type of wire. This wire appears to be bare copper, but it has thin coating of insulating materials. The wheels are sitting perfectly at the center of wheel well with even spacing all around and perfect alignment. And this is how the final product looks like. Firstly, let's see how everything looks like from underneath. It has enough torque to slip wheels even at low battery charge. The fastest it could go is about 1.4 meter per second or 5.04 kilometer per hour. Coincidentally, 5.04 kilometer per hour is also an average walking speed of humans. On sloppy surface, the max it could climb is an incline of up to 34 degrees or 67%. If you increase incline more than 34 degrees, then it starts to struggle, not because of lack of power, but because lack of traction. Our final test will be steering test. As I said earlier, the steering mechanism is turned to do understeer at high speed. The green circle represents the turning radius at high speed. The red circle is about 50% bigger and it represents the turning radius at low speed. Thanks for watching.